let us discuss about MOSFET or metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. So, the MOSFET basically, as the name implies, it consists of 3 layers. So, before we go into the MOS transistor, first let us see the MOS structure. It consists of 3 layers, one metal layer, one oxide layer and one semiconductor layer. Now, previously we used to use aluminum as the metal, but then we found that the metal to semiconductor work function difference is substantial. So, we these days, in order to reduce the threshold voltage of the transistors, we have shifted from aluminum to doped polycrystalline silicon. So, these days we use doped polycrystalline silicon in place of the metal in the MOS structure. So, in this MOS structure, we have doped polycrystalline silicon at the surface, followed by the oxide layer, which is typically a silicon dioxide layer, and then we have the semiconductor, which means the silicon structure. Now, if we apply a negative voltage across this MOS structure, let us consider that this semiconductor is formed of a p-type substrate. So, if you apply a negative voltage, what will happen? The holes will get attracted towards the negative potential, because you have electric field in this direction. So, the holes will move in this direction and they basically accumulate at the surface of separation between the oxide and the substrate. So, this phenomena is known as accumulation. Now, as you go on reducing the negative voltage, you will see lesser and lesser number of holes accumulating at the surface of separation between the oxide and the substrate for obvious reasons. Now, when you start giving positive voltages, what happens? The opposite thing will happen. So, the holes will start moving away from the surface of separation between the oxide and the substrate, and therefore, at the surface of separation between the oxide and the substrate, you are basically having a depletion region being formed. The thickness of the depletion region depends upon the potential being applied and the doping density. So, now if you observe the capacitance versus voltage characteristics of this MOS structure, then initially you have accumulation, where you have a good amount of charge separation between the metal and the semiconductor, and the oxide was acting as the dielectric. Then, because the depletion region is being formed, you now have the width of the distance between the plates of the capacitors being increased, and therefore, there is a fall in the capacitance in this depletion region. Then, as you go on giving more and more positive voltage, a time comes when the concentration of positively charged holes in this depletion region becomes so less that it becomes lesser than that of the electrons or the minority carriers. Then suddenly you find a sheet of negative charge being formed, and this surface turns from of separation in the oxide and the substrate changes from p type to n type. That is called inversion. This inversion is known as a strong inversion. So, again now the distance between the plates of the capacitors decrease. So, now you are basically having again an increase in the capacitance. Now, if we now move from the MOS transistor capacitor to the MOS transistor, then you are basically having two densely doped n diffusion regions in the p type substrate, and you take 2 electrodes over here. Now, at the as soon as you overcome the threshold voltage, you have a n channel being formed between the two n diffusion regions. So, you are basically having a sheet of negative charges being formed, and thus the strong inversion takes place. Now, over here if you give a positive potential at one of the n diffusion regions with respect to the other, then electrons basically move towards the source of the positive potential, and therefore, you are basically having a drift of electrons being set up. The n diffusion region which you connect to a higher potential, we call it the drain, and the other n diffusion region we call it the source. So, now when you maintain a positive potential at the drain with respect to the source, the electrons are basically drifted towards the drain. Now, if you consider the potential drop across the channel at the source end, you are basically having a potential drop of VGS minus VT across the channel. So, this is basically the potential drop across the channel at the source end. If you want to find out the potential drop across the channel at the drain end, that is equal to VGS minus VT minus VDS. So, you can find that the potential drop across the channel is more at the source end than at the drain end, and therefore, you can find that the channel is basically thicker at the source end and thinner at the drain end. So, the drain current equation of a MOS transistor, it is basically given by ID equal to mu n COX W by L into VGS minus VT into VDS minus VDS square by 2. So, in this equation, if you, as you can see that as you go on increasing this VDS, then the channel thickness at the drain end becomes lesser and lesser, and when VDS becomes equal to VGS minus VT, then the potential drop across the channel becomes 0, which means that the thickness of the channel at the drain end should become 0. So, if you see, but in reality we find that the thickness of the channel does not become 0, but beyond the a point which we call the pinch off point, there exists a strong electric field through which electrons are deflected with a very high velocity towards the drain, and therefore, conduction does not stop beyond the pinch off point. If you see the output characteristic of the MOS transistor, it is basically like this. So, this is VDS, this is ID. So, along the VDS axis, we are basically having ID equal to 0. So, this basically corresponds to the cutoff region, and then we are basically having this linear part is called the active region or linear region, and finally, where you find the ID becomes almost constant except for a small slope, we call it the saturation region. At the saturation, so this is basically the drain current equation at the active region. At the cutoff region, it is equal to 0. At the saturation region, it is basically given by mu n COX W by L into VGS minus VT whole square into 1 plus lambda VDS. So, the boundary conditions are, this is true for VGS less than VT, this is true for VGS greater than VT, and 0 less than VDS less than VGS minus VT, and this is true for VGS greater than Vt and 0 less than Vgs minus Vt less than Vts.